Okay, so let's go ahead and begin today. So today the lecture is going to be relatively short. Because really, what we need to talk about next, so you can do the final project, is the circuitry that goes around your Otter CPU that we call the wrapper. And most of what's in the wrapper you've seen before, like CP133. And the wrapper is provided if you don't design it yourself. That's something that Dr. Hummel put together, and it's something we give to you. And, you'll basically just have to hook it up to your CPU once you're done with hardware 5. Okay, so you don't need the wrapper until the final project. So where I want to start today is just some of the things we've already talked about, because remember, hardware 6, that's the next thing that's due. That's due a week from tomorrow, Friday, March 3rd. And then the final project, the hardware part of the final project, that's due the last class day of the quarter. So that's Friday, March 17th. Okay. So before we talk about the wrapper, what the purpose of it is, and some of the circuitry that's involved, I just want to reiterate some of the things we already talked about, just so keep it straight. What's hardware 6 and what's hardware 7, because sometimes people can get them mixed up. Okay, so what we talked about already and what is involved with hardware 6 is what was that? A week ago today, right? Meeting, let's see, this is meeting 12, right? So meeting 10. Okay, meeting 10. I outlined the control unit FSM that you would need for hardware 6. Okay. Should be in your notes, or if it's not, it's on Canvas. Now, we talked about the write-back state last class, but for hardware 6, your FSM doesn't need a write-back state, because hardware 6, you just want your Otter CPU to work for those 6 instructions that are in the sample program. Like, remember the sample program that you did the timing diagram for last time? Those are the only instructions that your Otter CPU has to be able to process for hardware 6. And there is no load word or load byte or load half word in that sample program. Now there's an LUI, but like we talked about, LUI doesn't involve the memory module, and it requires 2 clock pulses, just like all the other structures except for load. So for hardware 6, your control unit FSM, you don't need a write back. Okay, so it's just going to have your initial, your fetch, and your execute. And it just needs to execute 6 instructions. And like I said, I outlined, I gave you the state registry code, right? Because in your FSM, you get the always FF block, and that's where the the external reset's going to go. Okay, and that's where you have the line between present state to next state and so on. So I mean, I gave you that. And that's not going to change. That's going to be the change. That's going to be the same. Your state registry code and your FSM, that's going to be the same for hardware 6, hardware 7. Once you have that, you don't have to modify it in this way. Okay. In the state decoder, the FSM, we talked about the initial state. The only thing that happens in the initial state is that's when the program counter is reset. And so your PC reset make equal to 1. And then in the fetch state, that's when we're getting the instruction at the address that the program counter is providing. So in the fetch state, you just have that memory read enabled in the memory module. So really where the work is involved when it comes to the control unit FSM is in the execute state. Okay, because there, remember what the FSM is doing. The FSM is providing the read and write signal that you need for instruction. So this is a part of code where you need to have some knowledge about how to complete this and so on. That's okay. I'll bring it. Okay. And you have a control of the controller. And up there, also having again some knowledge of the instructions that remember that the Trojan controller, that's providing the month selects. That's routing the data, through the Otter, depending on the instruction. So you see that again, you're going to have knowledge of the function features and so on. Okay. And then you got the top one. Right? Now, let's have these control units, all coded models. Now you have all the pieces of Otter, right? So control units along with the other pieces are stored. Now you got to connect them all up. You talk on the construction model for approximately CP133. Now, what these designing is, you only run one box, right? You just have box over by the program. Right? There's three other options. And some of the ALU, and that box that's probably with the right. So again, like I mentioned, that's an option. You can put the muxes right, those three muxes right in the top module. You can put a case statement for each of the top module, or you could have a separate file, have this other science file. But two files. I personally think it's genius to put in the top module. There's no one way to do this. Everyone's hardware sets and also everyone's final project will be different. Now, for hardware sets, it's the same groups, two-person groups belonging to the same grading criteria as the previous hardware sets. There's no difference in the increments or grading criteria for hardware sets. Okay. Now, once you have this, right, once you've got this module, you're going to move it over to Dr. Home. Let me show you where it is. Dr. Home under meeting 11. It's titled Hardware 6, Dr. H. I think it's from the 26.5-minute mark on. It shows you the sim for hardware 6. Okay, so when you go to run the simulation in the auto for hardware 6, you will see it. Your Otter is running that program through the program correctly. You can watch this video also. This is the reason I have to do the timing diagram of really for that. You've also done it manually. You can also see if your timing diagram matches Dr. Hummel's simulation. Because the manual activity, right, you should match what he has. Okay. So, that's the process you get for hardware. Okay, so do you have any questions about hardware 6 before we move on? Like I said, what I would say is basically the talking about the wrapper, and then I'll also make comments about the final product. Deal with contrast with the final project hardware 6. See what's so yeah, that's the final project. The final project hardware. That's not hardware efficient still same device. Yes. Yeah, like I said at the beginning of the quarter, we're going to have in-person meetings up till Tuesday of next week, because Tuesday of next week, there's just a couple more software things I need to talk about. We have to talk about what that stack segment is. Like, remember in real memory, we've got the code segment, the instructions, the data segment that we talked about, but we haven't talked about the stack yet. And I say that for last because we're also going to talk about subroutines, and that kind of goes with subroutines. Not exclusive to subroutines, but it kind of goes with it. So yeah, Tuesday of next week, we talk about the stack and also subroutines. And then also Tuesday, I'll talk about the final project software. Okay, because, you know, I basically took the final project and I split it into two parts. You know, one part's through the 9th week, that's the software part. And this final project hardware where you got to have the whole auditor, you know, doing every instruction. That's due the last day for the quarter, because that's probably going to take most people the longest. The final project software, I'm guessing for most people, I don't think it will take that much. Okay, but we'll talk about it in detail.
So, and are written like online classes afterwards, or is that?
No, what I mean by, you know, like the in-person ending and like the online beginning, is that I'm available online during that time, and there's no new material. It's just that the last 2 weeks, the time is devoted to you to work on the final project in your either groups. You know, like I said, the hardware final project, you'll be allowed up to 4 people. The software final project is still 2 people. I'm assuming the same 2 people as earlier in the quarter, unless somebody wants to change. Yeah, so, yeah, the last 2 weeks, you're not required to come to class. There's no like formal class, but there's no new material. It's just time for you to work on the final project. And then a week from today, we just have an open lab. And that's, you know, people gotta, if they got behind and need to catch up, or, you know, it's an extra class to get it back. But we'll be done with the material on Tuesday of next week. And again, because we lost 2 classes, we weren't able to cover interrupts. You know, someone might say, well, why not use the open lab for interrupts? I could, but then I would have to assign something on it. Otherwise, really what's good about talking about it. And then also to include it as the final project, that's more work. And we just don't think it warrants the time. If we didn't lose the day of the storm, we could do it. It's not enough time to do interrupts.
What about like?
Yeah, attendance is just during the in-person. So yeah, like the open lab in the last 2 weeks, like I said, you don't have to come to class. I'm not, but I'll be available.
Okay. Like either conference or
Online.
online.
Yeah. I mean, there may be some days that I'm on. If I am, I'll let you know. I was thinking. Okay, any other questions before we move on? Okay, so now some new stuff. The first thing is, and this is on your diagram for the otter. Actually, I forgot to put otter diagram for the visual. I got enough for everything. But if you want your mom, you can. Okay, so on that otter diagram in the upper left-hand corner, I believe it is, it shows the high-level black box diagram for your otter CPU. You notice it only has, well, it has 4 inputs, but one of the inputs, the interrupt, we're not using. So you can either leave it out, or if you put it there, you can just connect it to 0. But you know, you just have our external reset coming in, an IO bus input, clock, and then you just set these 3 out: an IO bus right, IO bus out for data out, and IO bus address. Okay, so you know, in your top module, right? You model your top module for your Otter CPU. You're just going to have, you know, essentially 3 inputs and 3 outputs. Okay, that's all you need. That's all you need to declare. Okay. So, like I said at the very beginning of class, we have this auto wrapper. Okay, and the auto wrapper just refers to the circuitry that goes around your CPU that interfaces the CPU to the outside world. So it's going to interface it to our inputs and outputs. And this is the circuitry here. And again, this is provided to you. Okay, Dr. Hummel designed this. Now you will have to make a modification that I'll refer to coming up. And I show how or where in the file you need to make the modification in one of my videos. Because, you know, I already talked about this video here of Dr. Hummel's for Hardware 6, but there's also a couple more videos under Meeting 12, these two here. And I'll talk more about them later. But this one here I made, and in this one here, the Hardware 7 video that I made, I show where in this module, you know, you may have to make some modifications. Okay, and I'll get back to that coming up. But you see, here's your Otter CPU, and everything around it, that's what's in the wrapper. Okay, so you can see the wrapper has, what is this called? A MUX. You all know what a MUX is. Okay, it also has a divide by 2 circuit. So I think we talked a little bit about this previously, and you might remember this also from CP 133. The clock frequency of the Basis 3 board, what's 100 megahertz? Yeah, 100 megahertz. Okay, but we're going to divide it by 2 so that our CPU and the auto wrapper sequential circuitry is operating at 50 megahertz. Okay, you know, that's why we were using the 20 nanosecond period, like in the simulations, making our clock a 20 nanosecond period. The reason for this, the reason to divide by 2 is just to give a little bit more wiggle. Okay, you know, if we're running at 100 megahertz, your Otter CPU would have to be, you know, more efficient than if we're running at 50 megahertz, right? It's possible that someone's Otter CPU wouldn't run correctly, you know, would have like timing issues at 100 megahertz, but would be fine at 50 megahertz. Okay, so that was the reason for it, it's just to slow it down a little bit, to give a little bit of wiggle room in case your, you know, CPU is not the most efficient. You know, maybe you've got, you know, some added time to it. So it's just, again, to give some margin. Okay. Okay, now on the output side, now this is just the decoder for the 7-segment display that, you know, many of you probably even designed in CP 133, right? So this is just our decoder. What are these here? Yeah, flip-flops, registers. Now this symbol you haven't seen. Yeah, it's a reverse mux. It's called a demux. Yeah, but I don't know. Was that talked about in anyone? Oh, okay. So some instructors say I don't talk about a demux in my CP 133, but a demux just works the opposite of a mux. Right? A mux, you got one output, multiple inputs, and the select just chooses one of those inputs to connect to the output. A demux, you have one input, multiple outputs. The select line is just picking, you know, which output connects to that single input. So demux or reverse mux, it might be called. It just operates exactly opposite of mux. Okay. Now, if you take a look at this, the select line for the mux and also the demux, it's coming from the IO bus address. Okay, so there's an address here, and that should make sense, right? Because how do we know the inputs? Like, how does the CPU know the switches? Like, how does it identify switches? Like in your code, when you were inputting something from the switches, what did you have to identify it as the switches? Yeah, we have to have that address, what was it, 11 all zeros, right? So you see when this select line is 11 all zeros, it's gonna connect the input of the switches to the output, and that's what's gonna go to our CPU. I/O bus. Now you can see there's this other input just labeled inputs. That's just like a generic input is, if we're gonna add other inputs. The way that the wrapper, the default, if you will, code of the wrapper just has switches as an input, it doesn't have any other inputs. But if you wanted to add like a keyboard or some other type of input device, you could easily do it. Okay, you could easily just extend this mux and come up with another address. And in fact, in the video, well, I talk a little bit about it in my video, and then there's another video that's not showing that's up further on the page where Dr. Hummel talks about, how you could add inputs. Now, because we're not covering interrupts, we're just using switches for the final project. Okay, because if you were gonna use a keyboard, you would need to have an interrupt in order to use a keyboard. Okay, but like I said, we don't have time for that, so the final project just gonna be switches for us. Okay, now likewise on the output side, this DMUX also has its select line attached to the I/O bus addresses. And that's because the output devices are also identified by an address, right? You remember what address we used for the 7-seg? It's like 11 all zeros, and then I think it's 40 for the 7-seg, and then the LEDs was, I think that's the one, 4 zeros and then 2 zeros. Okay. Now, you can see here on the output side, before we get to where the output devices are, we have these registers. And that's just to hold the data that we're going to write to the output devices until we're ready to do the write. And you see the CPU has this output, I/O bus WR, which stands for I/O bus write. And it's not until this signal goes high and the address for our output device is here where we enable the register. Right, so if we wanted to output data to the 7-seg, we'd have to have the 7-seg address here, so the 114040, and this I/O bus write would have to be high. And that would enable, right, because that high of the I/O bus write would be connected through the DMUX to this enable here. And now the contents of that register would be provided to the 7-segment display. Okay, so really what the wrapper is just a mux, with a divided by 2 for the clock on the input side, and just some register, well, DMUX, some registers, and then this decoder for the 7-seg. But it's this circuitry, again, that interfaces your CPU to the rest of the world. Okay. Now, the modification that you'll have to make, maybe, and most likely, is that we're giving you the auto wrapper, and then you're going to have to connect your CPU to that auto wrapper. And it's likely that you didn't call the inputs and the outputs of your auto wrapper the same as what Dr. Hummel did. So the modification that you'll have to make, and again, I show like where in the code you have to do it, but you'll just have to make the names that you use for the inputs and outputs of your otter, be in the portion of the auto wrapper code that's making the connections to the auto wrapper. Okay, so that's the only modification that you'll have to do. Okay, it's pretty simple. Okay, so any questions about anything about the auto wrapper, its purpose, or any of the components that is involved? Okay, well, like I said, in addition to Dr. Hummel's Hardware 6 video, which is under meeting, which meeting was that? I guess that was meeting 11. Yeah, meeting 11. There's these two videos here under meeting 12, Okay, again, I made this video, and then there's another one here, that Dr. Hummel made. And these two videos are particularly important for the final project. You know, when you watch Dr. Hummel's video, he's gonna be talking about hardware 7. Okay, because, you know, if we had enough time, it would be like a hardware 7, and then the final project would involve interrupts, so it would be like an added thing. Well, for our purposes, when you watch Dr. Hummel's video, whenever he says hardware 7, he's talking about our final project. Okay, because our final project is basically the old hardware 7 along with, you know, an additional thing that you'll program it, which I'll talk about some more. But I just wanted to put it out there that when he says hardware 7, we don't have a hardware 7. Our hardware 7 is the final project. Okay. All right, so I am going to turn this projector off and lift the screen because I got stuff behind it here. But before I do, are there any questions involving what's on Canvas? Everybody could find this, right? You know where meeting 11 and meeting 12 are. Let's turn off the projector. Okay, so once you have hardware 6 all working, you now know about the wrapper, because again, the wrapper is not part of hardware 6. Okay, so you don't need the wrapper for hardware 6. The hardware 6, you're just doing a simulation on Nevada, not downloading anything before. Okay, you need the wrapper when you're going to download to the board. Okay, so the wrapper is only pertinent to the final project hardware. So let me just go through, you know, the approach that I would recommend for when you start working on the final project. Now, first of all, again, it's due 3 weeks from tomorrow, right? Because that's the last class day. And when you get to the final project, you're going to have to modify the control unit FSM that you have for hardware 6, right? Because hardware 6, you didn't need the write back state, because in that sample program for hardware 6, you don't have a load word or a load byte or a load half word. But for your final project, your CPU has to be able to process all instructions, right? All real instructions. So now you're going to need a write back state, right? Because you're going to have load instructions. Also, you're going to have to modify the execute state of the state decoder of the FSM, right? Because now you got more than 6 instructions. You're going to have, again, there's like 30 some odd real instructions. Okay, so you're going to have to go in there and modify that part of the control unit FSM. Also, your control unit decoder, right? That's providing all the mux selects. That's going to have to be worked on, right? That's going to have to be modified because again, it's got to do all the instructions now, not just 6 of them. Okay. Now, the good news is if your top module worked for hardware 6, it should work for the final project. Right? I mean, that order all connected together is the same for hardware 6 instructions as it is for final project, which is for all instructions. Okay, so you shouldn't have to do anything to the top module. Okay, it's just the control unit decoder and also the execute part, you know, the state decoder of the FSM that you'll have to be working on. So once you do all this, now you have to sim that order again to see if it's gonna work for all instructions. And you're gonna have mistakes. Okay, there's just no way around it. Okay, there's gonna be mistakes. You know, when I did mine, I probably had close to a dozen mistakes. Now, most of those were really silly type of errors, like I connected something in my top module incorrectly, or I remember like one thing I did is I had like a bit mismatch at like my immediate generator. Instead of connecting like 25 bits, I connected 24. I was off by 1, something like that. You know, most of them were really silly. I did have one like major problem that I was able to fix, but I really don't understand why I fixed it. And that was with my reg file, where remember we had the asynchronous reads that we're using assigned statements for, and that's what I did. And my understanding is in Vivada or Verilog or System Verilog,
you know, wherever you put an assign, it doesn't really matter because that's continually happening. But for some reason, and again, I don't know why, I had my assign statements for my asynchronous reads, I had it below the FF block for the synchronous write. And technically, my understanding is it shouldn't make a difference where those assigns are, right? But my reg file wasn't working properly, and it was something with the write that wasn't quite doing what it should do. And I was working on it, and I was looking at it. It's driving me crazy. And all I did is I took the assigned statements and I put it in front instead of behind the always FF, and that fixed it. I mean, it worked after that. You know, I don't know the reason behind it, but that's what it was. But I knew where the problem was, like from the troubleshooting, looking at the timing diagram, I knew it was in the reg file. You know, and finally I just said, well, let me try this. And it fixed it. You know, so it was just a weird kind of thing. I mean, most problems aren't weird like that, but you know, sometimes you just run into something like that. So because you know you're gonna have problems, right? There's gonna be errors, you're gonna have to troubleshoot. Dr. Hummel under meeting 11. So the same video that he made for hardware 6, except you know, for hardware 6, watch from 26 minutes, 30 seconds onward. But if you watch before this time mark, he talks about a lot of the things that are good for the final project. Okay. Also, Dr. Hummel made another video, and it's under meeting 12, specifically on troubleshooting. Okay, how you go about troubleshooting your otter once, you know, once you have it where it should be executing all the instructions. Okay, there's this file that we provide, this mem file. It's called all test. Okay, all underscore test. And as the name implies, that mem file will test every instruction. Okay, so the goal is, you know, that your otter is going to be able to run this all test mem file without error. Okay, and you know, we provide that mem file. Also on Canvas, there's the text file for that all test mem file. And when you get a chance, take a look at it because it's like 4,000 lines of code, right? So it's running through 4,000 lines of code to check all the instructions. And if something's not right, it goes to an error code, okay? And the error code is a address of an instruction, okay? The error code shows up at the output of the program counter. And the error code is 22C. And I have that memorized because I saw it a lot. So when you hit that 22C, you got a problem. And in this video, Dr. Hummel, you know, he does a few examples, like he purposely puts in like 5 or 6 different errors, you know, and he shows you how he finds, you know, where the error is. But more important than the particular errors that he shows, because, you know, chances are you're going to have some different thing that's wrong than what, you know, he's doing as examples. So the most important thing to get from that video is the process, okay? The process that you go through in order to find the problem, okay? When you're troubleshooting the otter, what you have to do is, you know, you got to be looking at your timing diagram on Vivado. And in the video, Dr. Hummel gives a lot of good tips about how you can make things easy on yourself, as far as, like, there's a way that you can group signals together. And then once you have them as a group, you can hide them or have them show up very easily. So that way, you know, when you've got like 50 signals on your screen and say you only want to look at 6 of them, you can hide everything except the 6 you want to look at. You know, so it's really handy when you're, you know, doing troubleshooting. So, you know, you're going to be looking at the timing diagram on Vivado. You're going to need this diagram, right? The otter diagram. You're going to need the text file for the instructions that it's trying to run. And then if you still, you know, still don't have a good grasp on the different instructions and what they do, you're going to have your instruction manual opened up also. Okay, and it's basically, you know, wherever the error is, you got to sort of look before that. to see where it went wrong. And, you know, you got to look at your timing diagram and you got to see, well, okay, this instruction, you know, it's adding these two things together and it's putting the result in this register. Well, did that happen? So on your timing diagram, you'll have to look during the execute state to see if during the execute state of that instruction, it had all the right values. And then if it did it put the result in the right place during the next fetch, right? Because you know how, when we went through that timing diagram activity, how when a register gets updated, it happens during the time of the next fetch state, right? It doesn't happen during an execute because it's synchronous. So those are the types of things that he points out in that video.
A quick question about when we hook everything up, we're gonna have it to the sub module, right? And the module, we have to go back to one of the sub modules, change something, the program counter or reg file or the, you know, or whatever. We make that change in the file, is it just the change on the top module as well? Or do we have to like reinstantiate?
Well, the top module is just going to have the code that makes the connections between the lower level modules. But you can, you know, you'll be able to go into a lower level module and make any change you want. Yeah. And then, you know, I think in the toolbar, you know, above your timing diagram for the simulation, I think there's like a button called refresh, where if you only make a code change, you just hit refresh and it takes all the settings that you still have, you know, and it just, you know, just runs it again with all those same settings. It just now has, you know, since you changed code, hopefully now it fixes whatever the problem was. Yeah. Yeah. You know, one of the things that Dr. Hummel says at the beginning of that troubleshooting video that is definitely true. I mean, I agree with him 110%. And that's troubleshooting is like one of the most important skills to have as an engineer. And really the only way you learn troubleshooting is by doing it. You know, if someone just comes and tells you what the problem is, you're not learning, right? So like I said, really the process that he shows is what's the most important thing. Okay, so what else did I want to say here? I think I talked all about that stuff. All right, so once your otter passes that all test mem in the simulation, then you move on to see whether it's going to pass that all test mem on the hardware, on your basis board. Okay, and that's where the auto wrapper comes in along with a constraints file, right? So once you have a successful sim for the all test, now you'll have to include the wrapper in your project, right? You'll have to connect your CPU up to the wrapper. You need a constraints file, right? Because that maps the inputs and outputs to what's on your basis board, like the switches and 7seg. Now, like I said earlier, we provide the wrapper and we also provide the constraints file that okay, so that's all on Canvas and just download it and just use it. And then in my video, I show you what it should look like on the basis board when it's running that all tests correctly. What you'll see in the video is that there's, let's see, there's 36 tests, I guess it is. Yeah, 36. And it keeps track when it passes a test on the 7-segment display. Like it starts at 0 and it will go from 0 to 24 hex. And 24 hex is what in base 10? 24 hex. What's 24 hex in base 10? 36. So it's going from 0 to 36, but it's doing it in hex, right? So you'll see, it'll start at 0, and also you'll see that LEDs flash from right to left. And you see every time an LED lights, that means it's passed the test. And when it passes a certain number of tests, like within a set, then it increments the 7-segment display. So it's basically testing every real instruction And some real instructions take more tests than others do. In fact, some real instructions take more than 16 tests. So like you'll see the LEDs go all the way over, and then you may see them come back, like not all of them, and then it increments. And then other times you'll just see 4 or 5 LEDs light and it will increment. Okay, so there'll be a series of tests, and every time it passes a series of tests, the 7-segment display increments by 1. So if your 7-segment display goes from 0 to 24, in increments of 1, that means that it's working on your basis board. Okay. Now, I highly discourage, because what tends to happen, this happens in CP 133 all the time too, is people will want to just go right to the hardware. They won't want to look at the sim first. They just go, oh, let's try it on the hardware, see if it works there. Highly discourage that, because, like I said, it's not going to work the first time. It's probably not going to work the first several times. You're going to have errors. So get it all working on the simulation first. Otherwise, you're going to be wasting your time generating bit files. Right? So wait until it's working in the sim. And again, in this video that I made, I show you how to make sure it's working in the sim. Okay. All right. So once your alt test has a good sim, once it's all working on the board, now the last thing is you want to program the Otter to do something, right? Because you got this thing you spent all this time on putting it together, right? Now let's program it to do something. And what I'm requiring as part of the final project hardware is that you just pick one of the assignments, the software assignments that you've already done this quarter, or you could pick one of the ones I did in class. Just generate a mem file and then show that it works on the Basis 3 board. Now, any of the programs that we did prior that involve switches, you're going to have to add some code to what we did, because you would have to add some sort of delay, right? Because let's say it's a program where you're inputting, like data from 3 consecutive switch inputs, something like that. Well, in between each set of data that you're inputting from the switches, you're going to need some kind of delay, right? And remember, we did that, in class, I showed you how you could make a delay with like a 10-second or a half-second or whatever it was. You basically just put it in a loop, right? And you figure out how much time it's going to take in that loop. Okay, so you would have to add something like that to something that you already had prior. But other than that, it can be exactly the same as what you did for an earlier assignment, or like I said, one of the ones that I did in class. In fact, what I did, just as proof that it could be done, because I wanted to make sure I could do it. I don't want to ask you something that I don't want to ask you to do something that I can't do, right? So I made sure I could do it. I took the program that I think I did in class, or was it one that you did? I don't remember if it was one that you did or one I did as an example, but it was the one where, based on the value of an input from the switches, it would either multiply by 2 or divide by 4. Was that one that you did? Do you remember that? Was that one of the software ones that you did? It was early on. So anyway, that's the one that I did. And I think I might have mentioned this to some people, at least earlier this quarter, that, I have a working Otter, it passes the all test in the sim, passes the all test on the board, and then, the program, right? That I programmed the Otter with, I checked it out in RARs, right? Made sure it was working in RARs, made the mem file and everything. And I think I told people, at least some people, that, when I put that program on the Otter, it wasn't working. That, I put the first value from the switches in, and, it was a value where it multiplied that switch data by 2 and it showed it on the 7-segment display, but it would never go back for the next switch data. It was like it was getting caught in an incident loop or something like that. And, it was driving me crazy, because I double checked everything. Again, my Otter works, right? It's running the alt test the way it should. It's working on the basis board, so I know the wrapper's good. Like I said, checked it in RARs. I even simmed that, example program on Vivado, made sure the sim for that was working right. Well, to make a long story short, because I contacted Dr. Hummel just to see if I was missing something, because I was like, this thing should be working. So anyway, I was like, okay, maybe my board, my basis board that I've used for many, many different designs, maybe something's wrong with it. So about a week later, I finally got another board. And I was like, well, before I try this other board, let me try one more time just to make sure it's doing the same thing. And it worked. So it was either something with a switch, maybe a switch contact was dirty, or maybe the program just had to be restarted, because I didn't try that. I didn't try just restarting the program, which sometimes works. So anyway, see, I mean, you can get weird stuff like that, but the key thing, another key thing with troubleshooting is you got to be persistent. Don't give up. If you're persistent, eventually it will work. I mean, you might not be able to explain why eventually it works, but eventually it'll work. Okay, so let me see here. Okay, so the last thing here, unless you have questions, is, and this came up in response to a question earlier, but I'll repeat it, that for the final project hardware, you are allowed to have a group up to 4 people. Now, if you're going to do that, if you're going to change whatever hardware group you've been using prior to the final project, let me know and submit it to me by Monday, March 6th. So you got a lot of time to decide, but if you decide before that, let me know so you don't forget to tell me, because I got to know if the groups change. Okay, so you can have a group of 2 still. So if you just want to stay in the current group, you can do that. You can have a group of 3, you have a group of 4, no groups of 5 or 6 or like that, just up to group of 4. If somebody wants to do it by themselves, they can, although I would not recommend that. Okay, it is a lot of work for one person. Now, the other thing that goes with this is you're evaluated on your troubleshooting. So you're responsible for finding what the problem is. Now, I will provide guidance if you ask me, but I'm not going to look at your code and tell you where the problem is. It's going to be more like, have you tried this? Okay, where is it failing in the code? Okay, did you look at the instruction before that? Is that instruction giving you the right values in the execute state? Like, I can guide you, but I'm not going to look at your code and say, oh, well, there's something wrong here. Okay, you got to find where the problem is. Okay? All right, very last thing, and this is the reason why there's a handout on everybody's table with 14 questions. That's an ungraded, what I call exercise. So I'm not going to collect it. I'm not going to grade it. And you can see here that I listed the 14 numbers. So during today's class, any person here can come up and write what their answer is for that particular question. And if it's a right answer, I'll put a check mark by it. It's not required to do this, but as I wrote, I'll get to your question in a second. It's not required to do this exercise, but as I wrote at the top here, and I mentioned this at the beginning, everyone's final project is going to be different. And in fact, I have 6 working Otters. I have the one that I did. I have one that Dr. Hummel did. I have one that an ISA for me last quarter did. So I got 3. Those 3 do not have interrupts, okay, like what we're doing. Then I have 3 more that have interrupts. I have a Dr. Hummel that has interrupts. I have mine that has interrupts, and I have Dr. Kyanis that's got interrupts. So I have 6 Otters that work. None of them are alike. I would say mine is probably the most brute forced way of doing it. My ISA is probably the next most efficient. And then Dr. Hummel's is amazing. Dr. Hummel, he does everything. So it's actually it makes me cry. It's so beautiful, especially compared to mine, it's like, but anyway, I bring that up because there's all kinds of ways to do this, right? There's the the brute force way of doing it is basically, having code, for every single instruction. And you could do it that way. But there's more efficient ways of doing it. And the people that do it in a really efficient way, they see the patterns, like there's various patterns. So that's what this exercise is showing you some of the patterns. And like I put here, by no means on this sheet am I showing like all the patterns possible. I'm just showing some of the like common ones, I guess. Okay, just to kind of get you thinking. Okay, so that's what this exercise is all about, is just to, kind of give you some ideas of what's meant by looking for patterns. But I don't want you to think that you have to use what I give you. Okay, you have a question? Well, well, what the test case would be is just that sample program. Yeah, so actually, I'm glad you asked that question, because that brings up that in the SIM file for both hardware 6 and your final project, it's very easy. It's just you want to set your reset not to be active. So basically just, have reset assigned to 0, and you still need to create a clock and initialize it to 0. But that's all your SIM file is going to be. Like, you're not gonna like list different test cases in the SIM file, because the test cases are essentially that program that's going to be a mem file. So it essentially, the mem files are the test cases, if you will. That's probably what you were, And any other questions before, because that's all I have for the lecture today. So the rest of the time is yours to work on hardware 6.